So these lectures are on matrices and determinants. They've been recorded live in autumn 2019. The notes and slides were created by the academic staff from the Mathematical Sciences at UTS, or University of Technology, Sydney. Let's start with definitions, as we should start with all topics, simply because definitions allow us to have a bit of, foundations to build on. So, a matrix is a rectangular array of quantities in rows and columns. And it is treated like a single quantity. And here we have several examples. So we've got here A and B, and you'll notice that these two matrices are not the same size. Your size is given as m times by n, where m is the number of rows and n is the number of columns. So in the case of A, we are looking at how many rows? Anyone? 3 rows, and it's by 3 columns. How about B? What would you say the size is for B? It's a live recording, but it's very quiet. We do have students here. So we have 2 rows by 1 column. And for C is 1 row, and we have 1, 2, 3, 4, 5 columns. And for M, we have 2 rows and 3 columns. Now, the numbers or symbols in a matrix are called the elements or entries of your matrix. We can use a double subscript. So our element can be indicated by the row and column. So in this case, we've only got single digits for our rows and columns. Therefore, I just have 2, 1. If you had double digits, you'd have to have a comma in there. But in this case, A21, we're talking about row 2, column 1. So row 2, column 1 is 8. B, row 2, column 1, well, it's B, but lowercase. And M, row 2, column 2, is -1/2. If we have a 1 times n, in other words, a single row times by a column, this is known as a row vector, whereas an m times 1, so we have like here or here, multiple rows and a single column, that's a column vector. So you've seen this before. I'm not quite sure what is happening here. That shouldn't be there, it's not in my original slides. So let's just scribble that out. Oh wait, it's not there. Okay. Now, there's a thing called equality of size, and your equality of size is when the number of rows and columns are the same. So it's said to have the same order of size if they have the same number of rows and columns. A square matrix has an equal number of rows and columns, but 2 matrices are said to be equal if and only if they have the same number of rows and columns, and each element in in the same position in those two matrices is the same. So if we look here, A is a 2 by 2, and so is B, and although they have a 1, 8, 3 and 4, so 1, 8, 3 and 4, these are not in the same place in the matrices. Therefore, these two are not equal. So we can write that A is not equal to B. So if matrices are the same size or same order, they can be added or subtracted. This is only valid if they're the same size or same order. And when it comes to adding and subtracting, we're adding or subtracting the elements that are in the same position. So here we have the sum, defined only if they're the same size. So we've got 2 plus 1, which is 3. 1 plus 0, which is 1. 1 plus 2, 3 again. 0 plus 1, which is 1. Minus 1 plus 3, so it's 2. 3 plus 1 is 4. The difference, or minus, 1 minus 1 is 0. 3 minus 1 is 2. 6 minus 1 is 5. 1 minus 1 is 0 again. Minus 1 minus 1 minus 2. 1 minus 1 is 0. 2 minus 1 is 1. 1 minus 1 is 0. Is this, however, possible? Because we have 3 rows, 2 columns, and 2 rows, 4 columns for the size. Is this possible? No, it is not possible. So someone in the audience has actually crossed their arms to say not possible. So we'll put NA. It's not possible as the size is different. Just because the size is different, you can't do it. So matrix addition and subtraction requires the same order or same size matrix. Any questions? Straightforward stuff here. So moving on, the rules of addition. Matrix addition is commutative and associative under addition. What this means is A plus B is equal to B plus A, as we have with normal arithmetic. And if we have B plus C and we add it to A, it will be the same as adding A plus B to C. So you can work out those first and add it to that, work this out and add it to that, you'll get the same. A zero matrix is any matrix with all elements equal to 0. So you can see here that all the elements are equal to 0, and it's usually written as a bold 0. And the thing with the zero matrix, assuming it's the same size, A plus 0, so a matrix A plus the 0 matrix is equal to 0 plus A, which gives us A, as we have found in normal arithmetic. Lastly, before we go on to matrix multiplication, if we multiply it by a scalar constant, so here we're going to use k. If we multiply it by k, then it's the same as multiplying all the elements by k. So 2 becomes 2k, k, 0 times by k is still going to be 0. Multiplying our 1s, they become k. Multiplying 0, 0, k, and then 2k. If we are multiplying two matrices together, this is a bit more complicated, and I'll cover that in the next broken segment.